Good morning, students. In last class, we have discussed regarding explain reactive power of capacitors in basics of capacitors, and also write a short note on capacitors connected in parallel, capacitors connected in series. And also we have discussed regarding the control of open circuit voltage with shunt reactors. But today we shall discuss regarding the what are the objectives and practical limitations of series compensation, and also we shall discuss regarding the power transfer characteristics, maximum transmissible power for symmetrical line with midpoint series capacitor and shunt reactor. And also in next class we shall discuss with the fundamental concept of compensation by sectioning. First, we shall see the objectives and practical limitations. What are the objectives and practical limitations? The main concept of series compensation is to cancel a part of the reactance of the line by means of a series capacitor. By using a series capacitor, series compensation, the main concept of series compensation is to cancel a part of the reactance of the line. Okay, by using what? By using a series capacitor. This increases the, if we use the series compensation, this increases the maximum power and reduces the transmission angle at a given level of a power transfer, and it increases the virtual natural load. Once again, I repeat, if we use a series compensation or series capacitor, it will increase the maximum power, it reduces the transmission angle, and it increases the virtual natural load. The line reactance reduces and now absorbs less of the line charging reactive power, often necessitating some form of shunt inductive compensation. The line reactance, what we use, the line reactance will be reduced if we use a series capacitor. Then it absorbs less of the line charging reactive power and often necessitating that is some form of shunt inductive compensation. Here, the series capacitor finds two main classes of application. Why we can use a series capacitor and for what purpose we can use a series capacitor. The two main applications are, one is it can be used to increase the power transfer on line of any length. It is used to increase the power transfer on a line of any length. Sometimes a series capacitor is used to increase the load share on one of two more parallel lines, especially where a higher voltage line overlays over voltage, that is lower voltage line in the same corridor. The main application is power transfer one. Second one is it can be used to enable power to be transmitted stably over a greater distance than is possible without compensation. Second application is power to be transmitted stable. Okay, we shall transmit the power, but we cannot transmit a stable condition. We can transfer the power stable over a great distance, that is for a longer transmission line we can maintain the stable conditions, we can maintain the stability also if we use a series capacitor. On a long lines, shunt inductive compensation is usually also necessary. For longer lines or for long lines, shunt inductive compensation is necessary because in order to limit the line voltage. A practical upper limit to the degree of series compensation is the order of 0.8, and they have given with Ks is equal to 1. The effective line reactance would be 0 for that condition. So, the smallest disturbance in the relative rotor angles of the terminal synchronous machines, if any small disturbance occurs in the rotor angles of the synchronous machine, okay, smallest disturbance in the rotor angles of a synchronous machines, that will result a flow of large current. Okay, The circuit would also be series resonant at the fundamental frequency, and it would be difficult to control a transient voltage and current during the disturbances. If that is the case, if the series compensation is order is 0.8 and KC is equal to 1, and the effective line reactance is 0 for that condition. If that is the case, so the smallest disturbance in the rotor angles of the synchronous machine, that will lead to a large current, flow of large current, and that circuit would also be series resonant at the fundamental frequency, and that will lead to a that is, in that situation it is difficult to control a transient voltage and current during a disturbances. Next, the capacitor reactance. The capacitor reactance is desired by the steady state and transient power transfer characteristics, as well as the location of the capacitor on the line. The capacitor reactance is desired by what? Desired by the steady state and transient power transfer characteristics, as well as the location of the capacitor also important. Its location is decided partly by economic factors and partly by the severity of fault currents. How we can decide the location of capacitor means the two reasons they are saying here. One, we can decide by economic factors, or we can decide by the severity of fault current, how much the severity fault current happening. On based on two factors, they will decide the location of the capacitor. The voltage rating is determined by the severity of the worst anticipated fault currents through the capacitor and any bypass equipment. The voltage rating, how they can determine the voltage rating is the severity of the worst anticipated fault current and also through the capacitor and any bypass equipment. In practice, lumped capacitors are installed at a small number of locations along the line. This makes for an uneven voltage profile as will be seen. Lumped capacitor lead to an uneven voltage profile. This is regarding the objectives and also the limitations. Next, we shall discuss the power transfer characteristics and maximum transmissible power. This is important. They may ask for 10 marks. First, ES, sending voltage, and ER, receiving voltage. I1, I2, and here we have splitted XCY, that is compensation is splitted. Okay, here minus J of XCY, minus J of XCY, V1, V2, and JX. Okay. Symmetrical with midpoint series capacitor and shunt reactor. This circuit is, and you can see here, this is the equivalent circuit with perfect shunt compensation, and this is the phasor diagram. First, we shall consider the left-hand line section, that is a sending end section. The conditions at it two ends are related by the fundamental equation, that is ES is equal to what we can write V1 cos theta by 2 plus J Z0 I1 sin theta by 2. This is the sending end side. And also we can write the current IS is equal to J V1 divided by Z0 sin theta by 2 plus J I1 cos theta by 2. These are the sending end side IS and ES we have written. The receiving end off of the line behaves similarly. What they are saying is the receiving end is behaves like a behaves similarly. Off of the line behaves similarly. The capacitor reactance XCY is equal to 1 divided by omega CY, and the voltage across the capacitor is given by what we can write voltage across the capacitor. Voltage across the capacitor V1, V2. So what we can write, V1 minus V2, that is equal to minus J into Im into XCY. Okay, even if you see the phasor diagram, we can write directly V1 minus V2, that is equal to minus J into Im into XCY. By symmetry, P is equal to what we can write, Vm into Im. Es is equal to Er. By symmetry, if we take that is P is equal to Vm into Im, midpoint voltage and midpoint current. If that is the case, Es is equal to sending equal to receiving end. So Vm is equal to what we can write, V1 minus of Vcy, that is equal to V2 plus of Vcy. Because we have said here the receiving end of the line behaves similarly. And the symmetrical condition, the current I1 and I2 are given by Im is equal to, similarly we can write for the mid current, that is Im is equal to midpoint current, Im is equal to I1 plus JV1 divided by X plus I2 is equal to I2 minus JV2 divided by X. Using this relationship and taking Vm as reference, midpoint voltage as a reference, it is possible to follow the same procedure as used to derive the basic power transfer characteristics. That is P is equal to Es into Vm divided by Z0 sin theta by 2 minus Xcy by 2 cos theta by 2 plus Z0 by X sin theta by 2 into sin delta by 2. This is we have derived in the topic, that is power transfer characteristics. P is equal to, this is a standard formula, Vs cos delta by 2 is nothing but Vm cos theta by 2 plus Z0 by X sin theta by 2, that is equal to Vr cos delta by 2. This can be written as Vs cos delta by 2, we have written this one. If Vm is substituted from equation 7 into equation 6, the following general result is obtained for the symmetrical line. We know that Es is equal to what? Es cos delta by 2. So Es is Es. We know the Vm divided by this value. So Es is equal to Er. We have Es into Er divided by Z0 sin theta minus Xcy divided by 2, 1 plus cos theta mu x close bracket into mu x sin delta. We have considered here if Es is equal to Er. So what is here? Mu x is nothing but 1 plus Z0 divided by X sin theta divided by 1 plus cos theta. That can be written as 1 plus Z0 divided by X tan theta by 2. In the absence of the shunt reactor, mu x is equal to, in the absence of the shunt reactor, mu x is equal to 1. With the fixed terminal voltages, that is Es is equal to Er is equal to E, the transmission angle can be determined from equation 8. The transmission angle can be determined from the equation 8 for any level of power transmission below the maximum. Once we know the value of delta, if we know the value of delta, Vm can be determined from the equation 7. Okay. If we know the value of here, if this is the condition, then we can transmission angle delta can be determined from the equation 8. From equation 8. Okay. P value we are not, that is only equation 8. This is the equation 8. From this, if we know the value of delta, we can find out easily. If we know if Es is equal to Er is equal to E, then we can find out the angle delta. Next, from if we know, once we know the value of delta, we can find out Vm easily. And V1, V2, Vcy other quantities can be found by using a equation 1, 2 and 2 equation 4. And next is the special cases. What is the special cases? By ignoring the shunt capacitance of the line and removing the shunt reactors by Ignoring shunt capacitance and removing the shunt reactors, then Z0 sin theta is replaced by XL and mu x is equal to 1, so that with ES is equal to ER is equal to E, then this equation will become P is equal to E square divided by XL minus XEY into sin delta. We ignore the shunt capacitance and we will remove the shunt reactor. Okay. And the Z0 sin theta is replaced by what? XL and mu x will be 1. If the degree of series compensation KAC is defined by KAC is equal to XCY divided by XL, that is equal to XCY divided by omega A alpha into L. If P is equal to what, it will become E square divided by XL open bracket 1 minus KAC close bracket into sin delta. So this is the form of the power transfer characteristics is useful because of its simplicity. Error resulting from the neglect of shunt capacitance. When the shunt reactors are chosen to compensate the capacitance perfectly, that is, if you choose the shunt reactants are chosen to compensate the line capacitance perfectly, then X is equal to Z0 sin theta by 2 divided by 1 minus cos theta by 2. From the equation 9, the shunt reactance factor mu x reduces to mu x is equal to secant theta by 2. Okay, mu x is equal to what, it will become secant theta by 2. And the power transfer characteristics becomes P is equal to E square divided by 2 Z0 sin theta by 2 minus XCY into sin delta. This equivalent circuit does not take into account the fact that because the shunt inductive compensation is concentrated, the line voltage profile is not perfectly flat even at a no load. What they are saying is this equivalent circuit figure C does not take into account the fact because the shunt inductive compensation is concentrated, the line voltage profile is not perfectly flat even at a no load condition. This is regarding the power transfer characteristics. In next class, we shall discuss with the fundamental compensation by sectioning.